So Association Quantum is here dedicated to spread the quantum knowledge. Today we have Dr. Salil Bedkihal with us, and we're talking about the history of quantum. If you want, you can follow us on all our social media, Instagram, Facebook, and LinkedIn, where we always share insightful posts about what quantum is up to now, and who is the next speaker and what's the next webinar that is coming up. And from here, I will transfer it. I'll stop sharing my screen. And I will ask Dr. Salil, can you share yours and guide us through your presentation?
Yes, indeed. All right, so can everyone see my screen now?
Yes.
All right. So thank you very much for inviting me to talk about the history of quantum. And it is quite exciting, this topic. You always, in the social media nowadays, you always hear about the achievements of quantum computing. But where did this quantum come from, right? That's a question. And what is the history of quantum mechanics? And I would like you to take through this exciting scientific process of discovering physical theories that I think hopefully you all will enjoy. So I work at Institute for Quantum Computing as a postdoctoral researcher, and I'm working at the moment in quantum annealing, trying to solve the complex optimization problems using quantum computing. I will come to that towards the end of my talk. Most of my talk will focus on the scientific process of developing quantum theory. So going back to the 14th century, and if you look at the work that has been done, in fact, not only in the Western cultures, but in all the other cultures, people knew about astronomy. They knew about the positions of the planets, and all of the agriculture and harvesting timetables were in fact designed, based on these empirical observations. So Galileo Galilei, in fact, conducted a series of interesting experiments on how different particles move in the gravitational field. And he did this famous experiment in Pisa where he released two masses from the top of the Pisa Tower, and he found that they almost land at the same time. So that was quite an exciting observation by Galileo. And then Kepler, who was an astronomer, in fact, he had a series of observations about the planets and how they move. And he came up with three empirical laws, which are called as Kepler's laws of planetary motion. And all of this data, which was gathered, the experimental observations, which were created by pre-Newtonian scientists, right? They turn out to be extremely useful for Sir Isaac Newton. He synthesized all of this information into a very meaningful mathematical insight. And as you can see that in classical theory, first of all, we can track the position of the particle, which is x of t here, and we can also track the momentum of a particle. So if you know, for example, if you fire a bullet from the gun, and if you know the position of the bullet, you know the momentum of the bullet, you know the entire trajectory, right? So you can use Newton's second law of motion, F equal to ma, where F is the force and a is the acceleration. And if you know the force acting, then you can solve this differential equation and you can get the trajectory of the particle. So Newton, in fact, using his ideas, he was able to explain the motion of the planets around the sun. For example, this figure on the left-hand side is a typical elliptical orbit of a planet, and the force acting between the planet and the sun, which is the green dot, is the gravitational force between them. And so if you know the force, you can actually calculate the orbit of the planet around the sun. And not only planets, you can do it for comets and all sorts of other particles. In fact, you can design the entire Mars mission just using F equal to ma. And that was the classical view, that we can determine the positions of the particles and their momenta, and we can create a trajectory. And this is quite common because that is how we perceive the world around us. We can locate the objects at a given position, we can calculate their velocities, and everything worked perfectly well. So the Newtonian physics was able to explain motion of the planets around the sun, motion of the other objects subjected to various kinds of forces, and you can do all the engineering using simply the Newton's laws of motion. Now, where did it break down? Okay, so if you know mechanical motions of an object, that was one topic which was satisfactorily addressed by the Newton's formalism. On the other hand, you know, the world around us is made up of matter, but then there is radiation, right? Light. And not much was known about light, in fact. Newton did some really cool experiments with prisms. So what he observed is that when the white light passes through the prism, it bends, in fact, and you see 7 colors, you see rainbow. And this was, at that time, it was quite mysterious of why this happens. So Newton, he proposed a very strange explanation that the light is made up of corpuscles called as particles. And he said that these different particles of lights have different masses, so these different colors would correspond to different masses. That was his explanation. But then, as you know, that light is reflected, if it hits the surface, it is reflected, or if it is refracted. For example, if you put the stick in the water, and if you look at the stick, then it looks a little curvy because the light changes its direction when it goes from one medium to another medium. And this reflection and refraction of light could not be explained by using Newton's particle explanation of light at all. So Newton's theory was discarded because it could not explain the reflection and refraction of light. And so Huygens, he came up with wave theory of light. And he said, light, it behaves like a wave, as if, you know, if you drop a stone onto the surface of the lake, it creates waves and it transfers energy from one point to another point to another point. And that is how this entire wavefront is propagated. So Huygens' theory was the wave theory of light. And using this, he was able to explain the reflection of light and the refraction of light. Yet, nothing was known about the character of light. Okay, so from 1629 up to the 1867 almost, nothing was known about the character of light, although people have measured the speed of light, and it was known that roughly it travels with constant speed. That's all. But the character of light was not known. Until in 1791 to 1867, Michael Faraday, who was in fact a goldsmith in England, and he did some series of experiments which led to revolutionary insights into the nature of light. And then Maxwell, in fact, James Clerk Maxwell and Faraday, they came up together with a coherent explanation of what light is, okay? And so the whole idea was that it was shown by the experiments of Faraday and then the theoretical mathematical explanation by Maxwell that light is an electromagnetic wave. So how does it work? For example, if you have a charge, electrical charge, then this electrical charge would produce some sort of an electric field, right? But when we think about electric charges, we think about positive charge and negative charge separately, okay? And we know that two like charges repel and two unlike charges, they attract. So this was known experimentally. And so the first equation here on the screen, all what it says is that electric field So the left-hand side is the electric field. You can think about this as, this is called as a divergence, but forget about the mathematics. All what it says is that if you have a distribution of charges, then it will create an electric field. But the second equation, it says that the divergence of the magnetic field is in fact zero. And what the second equation means is that whenever you think about magnet, you can't think about it as a north pole of the magnet and south pole of the magnet separately. It always, there is no such thing as a single pole of the magnet. It is always a dipole. That is what the second equation says. And these two equations, so these two equations were known, but these two equations, what the third equation says is that if you have an electric field, or if you have a magnetic field, and if you have a time varying magnetic field, so for example, in the electric motor, right, you have a time varying magnetic field, then it would produce an electric field. So whenever you have a magnetic field that changes in time, that produces an electric field. And whenever you have the electric field that changes in time, it produces magnetic field. And so electric field and magnetic field are the manifestation of the same phenomenon called as electromagnetic field. And this was the greatest achievement because when Maxwell came up with his equations, this theory of classical electromagnetism, it actually, the speed of light naturally emerged as a constant from this theory. So using these equations, Maxwell was able to calculate exactly the speed of light, and that is 3 into 10 to the power of 8 meters per second. And so Faraday and Maxwell's beautiful experimental and theoretical insights finally settled the issue about the nature of the light, that it is an electromagnetic radiation. It does not need any medium to propagate. It can propagate in vacuum, and it travels with the speed that is 3 into 10 to the power of 8 meters per second. And this was a great discovery because Newton thought that light behaves as a particle. Huygens then said that no, because you cannot explain reflection and refraction using the particle theory of light. And so he advocated the wave theory of light, but the character of those waves was not known. And Faraday and Maxwell, they established that light is an electromagnetic radiation. And using the Faraday and Maxwell's theory, you can again explain the reflection and refraction of light. And so it was conclusively established that light behaves as a wave. Okay. Now this is very important because this is how the classical electromagnetic theory of radiation was then used from there onwards to explain the various processes of how light interacts with the matter. But there is a twisting point here, and the twist comes with the black body radiation. So what is a black body? Now, typically, if you have any object, metallic object, then above the absolute zero temperature, it will radiate energy. And this is because all the light that is falling on it, okay, it will be radiated by that object. From the internal energy is converted into the light. And so all the objects, as you know, they radiate. But the black body is the one which is an idealized, there is no such thing as black body, but in science or in physics, we always like to have some ideal objects. And we look at the behavior of that ideal object and then try to compare that with the real objects. So the black body, the notion of the black body is the one that absorbs all the radiation incident on it, and it can also emit that radiation in all frequencies. Okay, so classically now, because as we know that electromagnetic radiation is not it can be it's just a, you can think about that as a wave that is coming and interacting with the matter. What people thought is that when you think about the radiation emitted by the black body, you can think about this black body is made up of tiny oscillators. So you can think about each constituent atom in the black body as some sort of an oscillator that is going back and forth, but it will emit radiation at all frequencies. And therefore, as the frequency increases, the intensity will also increase. And this view that came from the classical theory actually led to this catastrophe. This is called an ultraviolet catastrophe. So what it means is that the intensity would just explode as you increase the frequency. But that's not the case. When measurements were made on black body radiation, um, like people did experiments with black body radiation, especially Wien and Luma, what they found was that at low frequencies here, the behavior you can explain it using classical mechanics, but then the curve doesn't explode, but it rather has this form. And this form of the curve, you cannot explain it using classical mechanics at all. And that's where then Max Planck came with his assumption that energy is emitted in discrete quanta. And with this, he came up with this equation for the intensity as a function of the frequency or the function of the wavelength. And Planck's equation then explains the entire curve here, okay? And this constant is called as the Planck's constant. Now there is something very peculiar about it, that if this constant was slightly different than what it is, atoms and molecules and matter would not exist and we wouldn't exist. So there is something special which we still don't understand possibly. And so this constant is called as the Planck's constant. Okay, it has joule second, so it has units of energy into time. And so quantization of energy, look, in classical theory, particle can take any energy. So if you have an oscillator, for example, harmonic oscillator in classical mechanics, it can take any energy. But in quantum mechanics, now there is a quantization of the energy. You can think about it like this. Suppose if you have a guitar, right? And if you pluck the guitar string, what happens? You have the guitar strings, which is tied at the one end of the guitar, you have a bridge, which is some sort of a solid object. And when you pluck the guitar string, you create an excitation on the string, so it propagates. And then it is reflected back and comes, and then you see that the radiation that is going in, the wave that is going in one direction and reflected, they interfere. And so you call that as harmonics and overtones. And the harmonics and overtones essentially are some integer multiples of the frequency, which is the natural frequency of the vibration of the guitar string. Okay, so they can't just take any value. It is something very similar, that the energy is emitted, but it takes a discrete value. And this was extraordinary observation, because this is something completely counterintuitive to classical physics. Is why would energy be quantized, right? And so classical theory cannot explain the entire curve. It gives this ultraviolet catastrophe. On the other hand, quantum mechanics can explain the entire black body radiation intensity curve. And that was a big, big discovery. This was one of the best experiments, in fact, carried out in 1890s to 1895. So with this now, this is called as an old quantum theory. So this just says that energy is emitted in the form of discrete quantum. Okay. Now there was another very interesting experiment which was done in 1914, and it is called as a Frankenhurst experiment. And so the whole idea is that you have a vacuum tube here on this, the picture on the left-hand side, with A and C corresponds to anode and cathode. And this tube was filled with mercury gas. Now, when you pass the electric current, so the cathode will emit the electrons. These electrons, they pass through the mercury and they are collected at the anode. And so if you measure the electric current, then this electric current shows these spikes. So for example, if you increase the voltage across the cathode and anode, the current would steadily go up, and then it would fall, and then it would go up and fall again. And this was a fantastic observation. So Frank and Hertz's data for mercury shows essentially that there is a particular voltage here, which is about 4.9 electron volts or kilo electron volts, I suppose, for which the current actually drops, and then it rises again, and then there is again another value of the voltage that it drops. Why would this happen? Right? And this was another observation that atoms are emitting and absorbing. In fact, the electron emission and absorption processes, as you change the voltage, are occurring at typical values. This was another observation that the energy levels in atoms have somehow the discrete form. But there was no theory yet. Okay, this was another experiment that changed the way we look at the matter at the microscopic scales. So how do you explain all these phenomena? Now you have the experimental results which show that energies are emitted in the form of discrete quanta, or the energy levels even in the atoms seem to have some sort of a discrete structure. How do we explain these things, right? And this is where the imagination comes in, and that's the soul of theoretical physics, is that you have to be able to imagine things in a totally different way, totally crazy way. So now, if you look at, and someone had a comment, in fact, that the quantum theory started with Bohr's atomic model, which is partially correct. So in fact, let's look at the classical model of an atom first. So what is an electron? Classically, if you think about the electron moving around the nucleus, then you can think about this electron as a charge, right? Electron is a charge, and this charge is moving around the nucleus. So this is like if you take a string and attach a stone at one end and revolve it, right? It has a centripetal force. And because of its centripetal force, or centrifugal force in this case, the charge will be accelerated, right? And if you accelerate an electric charge, then according to classical theory, this charge will emit light. It will emit the radiation, and eventually it will lose all of its energy. So what would happen to our atom classically? Electron moving around the nucleus would radiate the energy, and atom will disappear. Okay, and hence we won't exist. But that's not the case. We exist, and therefore there is something going on here that allows electron to be in these orbits without radiating energy. And this was the genius insight coming from the Niels Bohr. He said that electrons can only occupy those orbits for which the angular momentum of these electrons is an integer multiple of Planck's constant. And those are the all orbits which are allowed orbits. And with this ad hoc hypothesis, he was able to explain, first of all, the stability of the atom. And if you now just take the Bohr's model, you can calculate all these spectral properties of the hydrogen atom, because hydrogen atom has just one electron, so it's the simplest atom. And Bohr's model actually explains the spectrum of the hydrogen atom very, very well. Okay, so the quantization condition that Bohr imposed on these the allowed orbits of these electrons, that actually explained the spectral characteristics of the hydrogen atom spectrum. And so this model is called a Rutherford-Bohr, because in the Rutherford model, it was a planetary model. You have the electrons moving around the nucleus. And the Bohr's insight was that these electrons cannot take any energy. In fact, their angular momenta are quantized, and they are in units of nh bar. So this was another this is another situation where the quantization condition actually saves matter from collapsing. So this was fantastic. But why quantization, right? How do these things, how can we put these things into a unified framework? So we still have to develop theory. And therefore, uh, first of all, uh, we need more and more experiments which show that the quantization of the energy is indeed the case. And this was another experiment on photoelectric effect. So photoelectric effect, if you have a metal, for example, and if you shine light on this metal, then there is an emission of electrons from the metal surface when you irradiate it with light. And the energy of the electron simply depends on the frequency of the radiation, okay? And there is a threshold frequency below which no electron emission can take place. Now, to explain the photoelectric effect, actually, you can't use, you have to assume that the light which is coming and is incident on this metal is not a wave, but is rather coming in tiny packets called as photons, right? So Einstein then explained the photoelectric effect here with the assumption that light is made up of corpuscles of photons, with the energy of which is given by the Planck's relation. So now think about the Planck relation that I had in the previous slide. It says that the energy of the photon is an integer multiple of Planck's constant, right? And so these are the packets of photons, and atoms can either absorb a whole photon or nothing happens. There is no in between. It can either absorb the whole photon or nothing happens. And with this, Einstein was able to explain the photoelectric effect. And in fact, he was awarded a Nobel Prize for his photoelectric effect theory. And so to conclude now, that the Planck's quantization hypothesis actually explains many phenomena successfully where classical theory failed. But now the question is, how do we reconcile it, the quantization of energy, in a mathematical framework, right? In theoretical physics, we have the experimental inputs, and then we have to develop a physical picture, right? That's the next part of the discovery process. So, another series of experiments in fact, by Davis and Germer, it created a final, it gave a final touch to this whole business of quantum mechanics. As you know, that if you have a light, and if you pass this light through the diffraction grating, for example, then you see dark and bright patches. This is something called as an interference of light, right? Two light waves, if they come from the same source and if you superpose them, then there are some points where the intensity of these waves is cancelled, and there are some regions where the intensity is enhanced, right? And that's why you see the dark and bright spots here. Now, light behaves as a wave, and it shows wealth of the different phenomena like diffraction of light, interference of light, or it shows reflection and refraction. But in some experiments, for example, the photoelectric effect, it behaves as a particle. I mean, it behaves more or less like a particle with certain energy rather than the wave. Now, if it is true that light can exhibit wave nature in some experiments and particle nature in some experiments, then all the other elementary particles, such as electrons, protons, and neutrons, they should behave exactly the same. They should be behaving as particles in some experiments and waves in some experiments. So just like the diffraction of the light, can I see the diffraction patterns of the electrons? Okay, because, so this was the Louis de Broglie's hypothesis that all matter exhibits wave-like characteristics. And in fact, he had a formula to calculate the wavelength, which is given by the Planck's constant divided by the momentum. And momentum is just mass multiplied by the velocity. So we can calculate the de Broglie wavelength, okay? So if we want to see the diffraction of electrons, all what we need to know is the de Broglie wavelength of the electron. And then we need to design a diffraction grating that roughly has this, the spacing between the grating elements is of the order of this de Broglie wavelength. And then you'll be able to see the diffraction. Because in order to see the diffraction of light, you have to pass it through the grating. And these gratings, they come up with small, you can think about slits in it. And if the separation between the slits is of the order of the wavelength of the light that is passing through, then it will show the diffraction pattern. Likewise, we need slits, but now for the electrons, okay? So Davison and Germer, the American physicist, they demonstrated the electron diffraction experiment in 1937. What they did was they first calculated the de Broglie wavelength for the electrons, which is of the order of 10 to the power of minus 10 meters. And then if you pass these electrons through a powder of nickel crystal, then as you know, in atoms, the crystals are made up of tiny ions, and these ions, there is certain spacing between these positive ions, and the spacing between the ions in the nickel crystal is of the order of 10 to the power of minus 10 meters. So that acts like a diffraction grating, and you can see the diffraction patterns of the electron just like the diffraction patterns of light. And this indeed confirmed that electrons can behave as waves in some cases, and they can behave as particles in some cases. And that was one of the biggest experiment, I would say, in the history of quantum mechanics, is that the electron diffraction was demonstrated. Now you see that we have a series of experiments with some phenomenological theory that is showing a consistent behavior of quantization and duality, the wave-particle duality. And this goes certainly beyond the classical viewpoint, and we need a completely new description of nature at the microscopic scale. Now, how do we describe this at the microscopic scale? And the second, we need an equation of motion, just like force is equal to mass multiplied by acceleration. We need something like that, right? So that we can predict the properties of the matter by solving that equation. And this is where Schrodinger introduced the equation of motion for quantum particles. So the whole idea of the Schrodinger equation, I will try to explain these mathematical terms in a simple way. The whole idea is that now, instead of thinking about the position and the momentum of the particle, we think about the wave, and we associate a wave function, in fact, with the particle. And this wave function then satisfies this equation. It is called as a Schrodinger equation, okay? So you can think about this as F equal to ma of quantum mechanics. So this is the equation of motion that in quantum mechanics. So I will explain these terms. I'm sorry for putting these mathematical equations, but they are essential to the point. So what this says is that a rate of change of wave function, because this is the derivative here, the rate of change of the wave function. And this on the right hand side, you have this term is related to the kinetic energy, but now it is not a number, it is an operator because it has this derivative here. And this term is called as potential energy. For example, if you think about the electron moving around the nucleus, then this potential energy would just be the the attractive potential between the electron and the nucleus. Okay, and the interesting thing is that these are all operators now. They are not just numbers, but they're operators, and they act on this wave function here. Okay, so for example, if you look at this equation, it's called as time independent Schrodinger equation. What it tells you is that kinetic energy and the potential energy, or all the operators, they act on the wave function. Okay, so this is the operator. It's like you have two numbers, 2 and 3, then the plus sign in between them is an operator that acts and it gives you the answer. So something similar. This is an operator here that acts on the wave function, and it gives you a number here, which is the energy, and this E is related to the energy levels of the atoms or molecules or whatever you're looking at, times the same wave function back. Okay, so if you solve this equation, then you get the wave function. And if you know the wave function, you can calculate all the other properties of the matter using that wave function. Okay, for example, if you take this equation and if you apply it to the hydrogen atom, now hydrogen atom has one electron, one proton, and we know what is the force between the electron and proton. It is the force of, they attract each other, so we know the force is inversely proportional to the square of the distance between them. So if you put that in this equation, you get these beautiful patterns of the electron orbits. So for example, if the electron is in the ground state, which is a state of minimum energy, then it is more or less spherically symmetric, as you can see. But then if you go to excited states, then this splits and you will get two lobes here. If you go to the further orbitals of the electrons, then you get 1, 2, 3, 4 lobes. And so this is fantastic, because what Rutherford had in his mind was that electrons are moving around the atoms in a rigid or circular orbits, but that's not the case. Now, what quantum mechanics says is that there are the different kinds of orbitals here, and this has to do with the probability of finding the electron at a certain position around the nucleus of the atom. I will come to that in a moment. But the key points from the Schrodinger equation of Schrodinger's work are that the position and the momentum, which are numbers in classical theory, okay, because you can measure the position of the object in classical mechanics and you can measure the momentum of the object in classical mechanics at the same time. In quantum theory, position and the momentum are the operators. So they are like big matrices, okay, and which is completely counterintuitive to what we are used to in classical theory, where everything is just pure numbers. Second, this equation, it is a linear differential equation, okay? That means if it has n solutions, then you add all of them, and that is also a solution. So this has interference effect inbuilt in it, okay? But this wave function, it can be real or complex, and that was one of the most discomfortable situation for Schrodinger, because how can this quantity be complex? And I will come to that in the next slide. Okay, and we still need to explain how can this be real or complex, or what does it mean? But physical and chemical properties of matter can be understood by solving this equation. And all the predictions of Bohr's atomic model, you can reproduce it rigorously mathematically by solving the Schrodinger equation. So if you solve this equation, you can understand the spectrum of the hydrogen atom. You can understand these orbitals, the different electron orbits in the ground state and the excited states. So that was a very good progress. In fact, it was an excellent breakthrough by Schrodinger, and he got the Nobel Prize for his work. But now there is one problem, it's not a problem, but it's kind of a discomfort that this quantity here can be real or it can be a complex. Now, I will explain to you what it means. For example, if you look at the, let's consider two-dimensional plane, okay, X and Y. So any point in this plane, P, has two coordinates, X and Y, okay? Now, I can represent that as a pair of numbers, right, X and Y, but I can write it in a complex plane where I is called as an imaginary number. And imaginary number is the one with this I is nothing but square root of -1. Okay, that is why it is called as an imaginary number. And you can write Z in terms of X plus IY. So this is an ordered pair, X and Y, which would represent a point in the plane. But then if you change the sign from plus to minus, that would also be a point. It would be X and minus Y, if you like. But this is still imaginary, and that is still imaginary. But if you take the product of these two, okay, then you get x squared plus y squared, and this number is always positive, okay. And what it simply represents mathematically is the distance between this point and the origin here, okay. So likewise, the wave function, it can be real or complex, so it's something like that. But if you take the wave function and its complex conjugate, so for example, if you take Z and its complex conjugate Z star, the product is always positive. You can do the same thing. The wave function can be complex. So you take the wave function and its complex conjugate, and the number that you get is always a real number and positive. And Max Born in 1954 interpreted this as a probability. So if you take the wave function and its complex conjugate, then this object is always a positive number. And this was the interpretation of Born, was that this is probability to find a particle in a given region of space. So for example, if you look at these orbitals here, then you can't say where is the electron exactly. All what you can say is what is the probability of finding an electron around the nucleus at a certain position. That's all what you can say. Now, this is completely different from classical mechanics, because in classical mechanics, you can say that the particle is at this position and particle is at that position. But here you can't do that. All what you can say here is that what is the probability that the electron is at a certain distance r from the nucleus. And Max Born, in fact, he received the Nobel Prize for this interpretation. And therefore, this is how the notion of probability came into quantum mechanics, that we cannot think about the position of the particle exactly. All what we can say is what is the probability that the particle had certain position, or what is the probability that particle had certain energy. That's all what we can say. And this was a twisting point, because it's completely counterintuitive to what we are used to think about the world in classical mechanics, right? So Max Born, this was a very important interpretation, the Born interpretation. And then, in fact, not only Schrodinger, but Heisenberg, he also formulated quantum mechanics in a slightly different fashion, okay? In Heisenberg picture, you don't have this wave function psi, but you have something called as an observable A, and these observable quantities, they will evolve, they will follow this equation of motion. Okay, you don't have to think about this technically. I mean, it's just a difference between the formulation of the Heisenberg and the formulation of the Schrodinger. It gives the same physics, but they have different ways of thinking about it. The important thing from the Heisenberg work was the uncertainty principle. And according to Heisenberg uncertainty principle, if you try to measure the position of the electron. So that means if the standard deviation in the measurement of the position is very, very small, then you will lose the information about the momentum. So you cannot measure the position of the electron and the momentum of the electron simultaneously with arbitrary accuracy. Okay? Now this has nothing to do with the limitation of your measurement apparatus, but it is something the way the nature works. And you can see that the product of this uncertainty, the standard deviation in the measurement of the position times the standard deviation in the measurement of momentum is greater than or equal to h bar, where this is the Planck constant basically. And as you can see, that Planck constant appears everywhere here. It's a fundamental constant of nature that just appears in all the equations of quantum mechanics. So this was another breakthrough, that you cannot measure simultaneously the position and the momentum of the particle with an arbitrary accuracy at all. Okay, this is something if you come from 16th or 17th century, you would be highly, highly uncomfortable about this. But unfortunately, that's the way nature works. And then the next development that came around the same time was that Dirac equation. So if you look at the Schrodinger equation here, one thing that you will notice, now this object on the left-hand side is called as a derivative with respect to time. And this object here, that the inverted triangle square, it is the derivative, but with respect to space, like x, y, and z. And so here, this is the first derivative in time, and here that's the second derivative in space. So they are not treated on equal footings. That is because Schrodinger equation is only applicable to those particles which are traveling, the speed of which is very, very less than the speed of light. But if you have a particles, when they travel with the speed which is very close to the speed of light, not the speed of light, but close to the speed of light, then the equation of motion has to be, it is different. And that equation was invented by Dirac. In fact, he just guessed this equation first. And that was a genius stroke of Dirac, that he just guessed it. And this equation, as you see, you have mc square here term, which is a very famous Einstein's equation, right? E equal to mc square. So you have mc square, and then this is the same, it is the similar wave equation that of the Schrodinger, except that it is now applicable to those particles which are traveling close to the speed of light. And from this equation, two predictions came out. One is that electron has spin. It behaves like a spin in a sense. You can think about electron as a tiny bar magnet that has two poles, north and south, but it is something there. I mean, it has this spin associated with it. And the second was that if there is a particle, then there is an antiparticle. So the two predictions which came from the Dirac equation simply was the spin. It came naturally in this framework, and the prediction of the antiparticles also was naturally came. And this was a big breakthrough, because as you must have heard about in medical science, people use something called as a PET scanner. It is called as positron emission tomography, which is used for medical imaging. And these positrons, they are like electrons, except they have positive charges. And these positrons were predicted by Dirac equation. So you see that the quantum mechanics has helped quite a lot for medical science. And this is something, a genius stroke of Dirac. Okay. So Dirac equation was in 1933, and Schrodinger and Dirac, they both actually shared a Nobel Prize for a new form of the atomic theory. That is an atomic theory using the quantum mechanical wave equations of Schrodinger and Dirac equations. So that was a significant advance that now we can understand the structure of the atom using quantum mechanics. Now, and then Feynman came. Now this was another development. So the quantum mechanics, the way it was formulated by Schrodinger and Heisenberg, the equation of motions, Richard Feynman had a very different view about it. He came up with a path integral interpretation of quantum mechanics, and I will explain what it is. So now suppose you have an electron here, electron source, like an electron gun, and you have two slits here. So this is the 1 and 2. Now, so if the electron passes through these both slits at the same time, right? That's the beauty of quantum world, that it can go through both slits at the same time. So it interferes like light, and you see the interference patterns here on the screen. So the probability that electron arrives at the screen, you can calculate that quantum mechanically. And for that, electron has to go through both these slits at the same time. Now, what if you have three slits? If you have three slits, 1, 2, and 3, well, then electron comes through these three slits at the same time. If you have four slits, if you have n, it will be in n, it will pass through n slits at the same time. And that's how the Feynman thought that it just takes all the paths. And so his interpretation was that, and this is a cartoon picture here, that this is your birth and that's your death. And you take various paths in your life, okay? And your life is just sum over all these paths. Now that's a cartoon representation of path integrals. What it means is that there is a path that classical mechanics says electron should take, but then there are all these alternative paths which are quantum mechanical in fact, and the probability to go from one point to another point, you have to consider all these paths, infinite number of paths in principle. Okay, this is another interpretation of quantum mechanics which Feynman introduced in fact. And this was very useful to think about the elementary particle processes. So for example, in certain reactors where people do these experiments where they bombard the elementary particles with very high energies, and they look at the production of new particles, right? To explain those processes, Richard Feynman, in fact, formulated quantum mechanics in a diagrammatic fashion. So for example, here you have electron, here you have a positron, and they annihilate each other, and then it emits a photon. So these diagrams are called as the Feynman diagrams, and that was his contribution. In fact, Feynman has three contributions. So first one is the path integral representation. Second, quantum electrodynamics. Remember, I explained earlier that Dirac equation describes the electron and positrons, both the particles and the antiparticles.
Doctor, sorry, I'm sorry to interfere, Doctor, but I just want to let you know we just have a few minutes, and it's okay if you want to go a little bit over. We just need to notify our attendants just so they know what to expect. So we're about 5 minutes, or a bit less. Where are we at, so we know to tell our attendants where should we?
All right, so I will quickly go through this slide and then
Not a problem. There's no rush. So just tell us it's about another 10, 15 minutes.
Okay.
Okay, perfect. So for that, all the attendants, we're going a little bit extra. It's okay. Put your questions in the Q&A section. We'll try to address them, but we're going a little bit over our time. So stay tuned, and hopefully you keep enjoying with us and you don't have to run. If you do have to run, the recording will be available on associationquantum.org. Keep going. I'm sorry for interfering.
So what Richard Feynman did, he took the Dirac theory, Dirac equation, because this equation describes electrons and positrons, both. And you know that when electrons, or in general charged particles are moving, they produce the, because it has an electric field associated with it, it produces the magnetic field. So indeed produces the electromagnetic field, right? And so whenever there is a motion of a charge, there is an electromagnetic field associated with it. And what Feynman did, he constructed a theory of light and matter interaction using relativity, of course, called as quantum electrodynamics. And then his theory was able to explain the interaction of light and the matter in a successful fashion. Now, so that was the contribution of Richard Feynman, so path integrals and quantum electrodynamics. Now, and this was a big step. He received a Nobel Prize, I suppose, at the age of 25 or 26. So that was one of the greatest achievements, one of the finest, youngest physicists who received the Nobel Prize for his contributions. And so now there were some objections to quantum mechanics. And this is interesting. Einstein never agreed to quantum mechanics. He always thought that quantum mechanical description of reality is not complete. He was very uncomfortable with the idea that you cannot determine the position and the momentum of the particle simultaneously. And so he thought that quantum mechanics is incomplete and there are some hidden variables which you don't know, but if you know about those hidden variables, then you can determine position and momentum simultaneously. So he was extremely uncomfortable. And so Einstein, Podolsky, and Rosen, they wrote this paper on, can quantum mechanical description of physical reality be considered to be complete? Okay, and according to them, it was incomplete. And then in 1964, John Stuart Bell, this was one of the genius stroke, in fact, by a mathematician and a physicist, Bell. He said that no, quantum mechanics is incompatible with local hidden variable theory. So he ruled out the local hidden variable models. And so quantum mechanics is non-local. He established this non-locality. And this means quantum mechanics is not incomplete. Possibly, this is how the nature works at the microscopic scale. So this was the classic paper by Bell, which kind of countered the objections from Einstein, Podolsky, and Bohr. But Einstein, Podolsky, and Rosen. But notice that Einstein used quantum theory to explain the photoelectric effect. Yet he was uncomfortable with quantum mechanics. Now this is quite interesting. And it turns out in this case that Einstein is not right. There are no such things as local hidden variables, and quantum physics is the way it is, that you have to live with the discomfort that Einstein had about the uncertainty principle. So, with these developments, then once the quantum mechanics was established firmly, then Richard Feynman, he gave a lecture in Caltech on quantum. He came up with the concept of quantum computing, and he simply thought a computer where all of the computer elements are following the laws of quantum mechanics rather than classical mechanics. Okay, and his argument was that nature is not classical, it is quantum. And so if you want to simulate nature, like if you want to understand the properties of atoms and molecules, you can't do that on classical machine. You need a quantum machine. That was the Feynman's lecture on the vision of computing. Now, why quantum computing? I mean, why would quantum give an advantage? I will explain it in a simple language. In classical machines, you have bits, which are 0 or 1. For quantum, you have 0 and 1, but you could be in 0 and 1 at the same time. So this or in classical mechanics is and in quantum mechanics, 0 and 1 at the same time. What it means? Suppose if you again consider the double slit experiment that we had, then you have an electron coming in, and it can go through the slit 1 and 2 at the same time. If you think about it classically, then you would say, well, the probability to go through either slits, it's simply equal to probability to go through first slit plus the second. But quantum mechanics says no, it goes through both slits at the same time. And so if you can compute the probability quantum mechanically, then you have in the oval shape, this term here, the psi first and psi second, times the phase. I mean, there is some phase relationship between them. And the way you compute probabilities in quantum mechanics is completely different, right? It goes through both slits at the same time. So you can think about the zeros and ones. For example, this could be the spins associated with the electrons. And then on the circle here, you see 0 on the north pole and 1 on the south pole. But when they are in the, both zeros and 1 at the same time, that's the state here. So it's in both states at the same time. This is called as a quantum superposition. And then the probability, if you measure it, then it will be either in 0 or 1, but otherwise it's in the superposition of zeros and ones. Now, if you have 2 qubits, okay, so for 1 qubit, I need 2 numbers, okay. So what is the probability that it is in state 0 is half, 1 is half, okay. If I have 2 qubits, how many numbers do I need? So possible case states for the 2 qubits is 0, 0, 1, 1, 1, 0, and 0, 1. But it is the combination of all of these 4, right? So you need 4 numbers, alpha, beta, gamma, and delta. So 2 qubits actually contain 4 bits of information. This is quite interesting. 2 qubits can contain 4 bits of information. So if I have n qubits, I have 2 to the power of n bits information. So if you have just 300 qubits, so if you have 300 electron spins, you have 2 to the power of 300 bits amount of, you can squeeze all the information in the possible extent of the universe in this space. So there is tremendous advantage of using quantum, because you could be in all these states at the same time. It's like a big quantum interference where computation can happen all possible ways at the same time. And that's why quantum computing is expected to give a speed up compared to the classical machines. Now, for those of you who might be interested in what is going on in the industry at the moment, so in industry, there is this company called as a D-Wave, which was founded in 1999. And this company is working on solving the complex optimization problems. So for example, traffic signal optimization or drug delivery. I will explain one problem very briefly. Suppose if you have this graph on this here, okay, you have the red and blue vertices. And if I give you such a set of vertices, and if I ask you to find out the subset for which no 2 vertices are connected by an edge, these vertices are all not connected by an edge with each other, then this problem is very hard problem. It's called as an NP complete problem. That means classical machines, this is intractable for classical machines. And to solve such problems, quantum mechanics or quantum computing, the aim of the quantum computing is to solve such problems where classical machines will not be able to find the solutions. And so what D-Wave, they have designed this device called as a quantum annealer, and it works according to the following way. So you take the optimization problem that you want to solve, and you map that problem in terms of zeros and ones. Okay, so it's called as mapping to zeros and ones. It's called as an Ising model. And then because you want to find the optimal, you want to optimize, you want to find either the minimum or the maximum of the function, right? So this is done in classical mechanics. Then these minima or maxima, you can think about these minima or maxima as the barriers here. And then in classical mechanics, if you want to cross the barrier, you need to spend enough energy so that you can jump from this barrier. But in quantum mechanics, you don't have to. There is something called as a quantum tunneling, where even if the particle doesn't have enough energy, it can escape from the barrier, and this has to do with the wave nature in some sense. So quantum tunneling is supposed to give an advantage here over the classical computing, where you would need the energy to jump from this barrier. So this is where the quantum mechanics is expected to give an advantage. Okay, so this company was founded in 1999, and it is working on quantum annealing for problems which are relevant to finance and drug delivery. And finally, this is the last slide I have. IBM, they have in 2016, they built this IBM Q system, which is a quantum computer here, and it is available via cloud. Okay, so they do the consulting where scientists and businesses can come together, and you can run some problems on the IBM quantum computer, especially in chemistry and finance type of problems. Oh, I'm sorry, I have one more slide. And this is the recent breakthrough by Google. So they have this processor here called a Sycamore processor. And this processor, in fact, was able to solve a problem which classical supercomputer would take about 10,000 years. Google processor was able to solve this in about 200 seconds. So that's the recent breakthrough. It's called as quantum supremacy experiment by Google. So you can read about it more on the Google website. And finally, if you are interested in the detailed history of quantum computing, then there is this resource available where you can have the timeline of quantum computing. I could not cover all of this timeline in this talk, but you can certainly go through this website and look at the timeline of quantum computing. So with this, I would like to say that quantum mechanics offers the exciting possibilities of computing, because particles can be in all states at the same time, and this quantum interference phenomenon offers great speed up, and therefore people are working on quantum computing because they want to solve all of these problems which classical machines will not be able to solve. And with this, I would like to stop and take your questions. Thank you.
Amazing. Thank you very, very, very much for your presentation. We were glued to the screens. I got a few messages how much people enjoyed it. And we would like to ask, while you stop sharing your screen, in the meantime, tell us in the comments, what was your favorite part about this presentation as we stop sharing the screens and we'll start asking questions. What was your favorite part of this presentation? So just stop sharing your screen. You have an option on the top that says stop sharing. There you go. Amazing. Welcome back to us. Okay, so I have here a few questions, and we'll just keep it very, very short because we're already over time. And for everybody, again, the recording will be available for you. And you can always ask more questions after we'll send you the questionnaire. That way we'll be able to address them in our next webinars. So some of the questions that we have here, for an example, how can we connect between classical machines and quantum machines? What do you think about that?
Now it depends on the meaning of connect. So what do you mean by connect? It depends on the meaning. Well, let me elaborate this point. Quantum computers are not the replacements for classical computers. So for example, if you're browsing your Wi-Fi or watching movies on your laptop, quantum computers are useless because quantum computers then will be very slow. See, the advantage of quantum computers is that to solve a hard problem, it requires less number of operation, although the operation time, may very high. It requires less number of operations to complete a certain task as compared to the classical machines. And therefore, quantum computers are at the moment only useful for solving the hard optimization problems. So
Okay.
they are not the replacement, in a sense, for the classical computers, at least.
Okay. Okay, great. Thank you for your question. Another question we have from Amir. And Amir is asking, going back to your slide of hydrogen energy levels, can you explain what is the D column is? Because he said he have never studied this before.
Okay, so what does it mean is, let me go back to that slide. So what it means is, if you consider the hydrogen atom, it has one electron and one proton, okay? So the state of the electron in the hydrogen atom is characterized by a principal quantum number called as n. And this n, basically it would describe the principal quantum number. But then there are orbital angular momentum quantum numbers, because electron has orbital angular momentum. And so when L equals, that number is called as L. And this L actually goes from 0 to n minus 1. So for example, if I think about the n equal to 1, for n equal to 1, you have L equal to 0 only. So that means you're in a ground state and it would look spherically symmetric. Now, if I go to the excited state, or if I go to another level where the n is 2, then L would go from 0 and 1. And that means this is called as a p orbital. And then you have, because it is an excited state, as you can see, that it's not spherically symmetric, but it has a one lobe and then it crosses and it has another lobe. If I go to n equal to 3, then L, which is called as the orbital angular momentum quantum number, that would take the value 0 to n minus 1. So if n is 3, it will take 0, 1, 2. And that is this D coming from. And that's why you have 1, 2, 3, and 4 lobes. So the SPD orbitals actually are related to the angular momentum of the electrons.
Okay, great. And we'll finish on one more question here. Let's see, Hardik is asking how physicists, have physics creating a quantum algorithm?
Oh, okay. Creating a quantum algorithm, that's quite an interesting process. I mean, I have to answer this question in a very simple and layman's language. So the whole idea is that in order to carry out a computational task for a computer, you need to design 4 operations called as gate operations. So for example, in classical computing, this is called as a logic gate, right? You have 0 and 1. So you have 0 and 1, 0 or 1, and you have 0 but not 1, or you have 1 but not 0. And then there are 4 gates associated with these states called as logic gates. So in order to design a quantum algorithm, first you have to design these gates, right? And then you have to embed your problems on these gate operations. Is that how would you perform these gate operations? So for example, if you want to do 2 plus 3 equal to 4, then 2, you can represent that in terms of a binary number. 3, you can represent that in terms of a binary number. And then addition operation, you have to represent that also in terms of some logical operation. The same thing would apply in quantum mechanics, except you are in 0 and 1 at the same time, and therefore you have to define these operations using something called as quantum gates. And then the set of operations, you have to transform it into how these gates will act. And that is how you define a quantum process. So designing the algorithm essentially then you want to optimize how many number of gate operations you want to perform for a given task. That is roughly the approach. That's one way to design quantum algorithm. And the second way to design quantum algorithm, which is called an adiabatic quantum computing. So there you don't use gates, in fact. What you do there is you take your optimization problem and you represent that optimization problem in terms of ones and zeros, binaries, which are called as spins, okay? So you, for example, if I want to solve the problem to go, if you have n number of cities and I'm a salesman, and if I want to go from one city to another city such that I don't want to visit one city twice, okay, what is the optimal time? So you take this problem,
Yeah.
you have cities and you have connection between them. So you take this big graph and map it into zeros and ones into something called as an Ising model. And now you want to find the optimal time. In this case, that would correspond to finding the minimum energy state of this Ising problem. And to find that minimum energy state, then you can take another quantum system, which is easy to prepare, okay? And then you evolve the whole system such that the solution of one is mapped onto the solution of the other as you go very, very slowly. And then you end up in the desired ground state, and then you read the output, and that would correspond to the problem of your optimal.
That's great. Well, thank you very much. I know we have a lot more questions. We'll keep them and for next time, and we'll look at what are your questions and try to cater our webinars and our panelists accordingly. We don't forget, we'll have a questionnaire coming out as well. We'd love to hear, please fill it up. We'd love to hear your thoughts so then we can serve you the best way. I'm going to share my screen one more time, just explaining you a few things, what's coming out. Stay tuned for another 2 seconds. Thank you so much for your presentation, for being here. Greatly, greatly appreciate it, and we loved it. So here I go, I'm sharing a screen. So as mentioned, Association Quantum, we here dedicated to spread the quantum knowledge. We looking forward for our next webinar that will happen in about 2 weeks, Quantum Beyond Quantum. Register, the Eventbrite is open, the meetups are open as well. You can follow us on all our social media platforms, register to our newsletter at www.associationquantum.org to make sure that you get once a month a newsletter that tells you what's new in the quantum world and what is the webinars that we are hosting to try to educate you about the quantum world and what's happening in it. So on that part, I will conclude. I'll stop sharing again. And we'll conclude. And again, thank you everybody for attending. Thank you for your comments. The Q&A section was exploding. The chat was exploding with wow, and this was amazing. And people said some of the things they never learned before. So that's great. Thank you so much for joining us. And thank you for your presentation. Thank you for your participations. And we'll see you in the next webinar.
No problem.
Have a great afternoon or evening wherever you are.
Have a good day, and all of you should stay safe. Thank you.
Thank you very much. Bye.